Dear students, Assalamu alaikum. So this is going to be our lecture 13 for Engineering Fluid Mechanics MAE 225, and today we are going to review the Bernoulli equation and see some applications of Bernoulli equation through problems in our textbook. So without delaying any further, we will move on towards the review of the Bernoulli equation first and then see the problems. So on your screen, you can see Bernoulli equation in three forms. The first equation has a form P over rho plus V square over 2 plus GZ is equal to constant. It has a units of meter square per second square, or in British gravitational, it has a British gravitational system. It has a units of feet square per second square. The second equation has units of pressure, that is Newton per meter square or pound per feet square, that is also written on your screen. The third equation is can be called as Bernoulli equation in the head form. It has units of length, that is meter in international system of units, and feet in the British gravitational system. In order to apply Bernoulli equation, you must make sure that you apply Bernoulli equation in conditions under which it was derived. So while deriving Bernoulli equation, we assumed that the flow is steady state, uh, the flow is incompressible, the flow is inviscid, and the flow is along a streamline, or the 2 points along which the Bernoulli equation is written are along a streamline. So we must make sure that we apply Bernoulli equation when we can assume the flow to be steady state, incompressible, inviscid, and along a streamline. So as an example, we see problem 3.24 from our textbook. The problem statement is also on your screen. It goes like: a pitot static tube is used to measure the velocity of helium in a pipe. The temperature and pressure are 40° Fahrenheit and 25 psia. A water manometer connected to the pitot static tube indicates a reading of 2.3 inch. Determine the helium velocity. Is it reasonable to consider the flow as incompressible? Explain. So we are being given the properties of helium that are flowing in a pipe, and we are being told that a pitot static tube is used to measure the velocity of helium in pipe, and shaped U-shaped manometer or U-tube manometer reads the pressure difference between 2 points to be 2.3 inch. So we have to find out the velocity and tell whether we can assume this problem to be incompressible or not, and explain as well. So a pitot static tube is a device that measures velocity with the help of pressure difference. Pitot static tube measures two pressures. One is the static pressure, and another one is the total pressure. Uh, and with these two pressure differences, we can find out the velocity of the flow by applying Bernoulli equation. So the figure that just appears now on your screen actually shows helium flowing in a pipe with a temperature of 40° Fahrenheit and a pressure of absolute pressure of 25 psi, whereas the velocity of the helium is unknown. Uh, the U-shaped manometer is connected to two tubes, which are actually pitot static tube, and it actually tells difference between pressure of 2 points. So in order to find the unknown velocity of helium inside the pipe, we apply Bernoulli equation between points 1 and 2 that are shown in the figure as well. We assume that points 1 and 2 lie along a streamline. The flow of helium inside the pipe is steady, i.e. it is not a function of time. Um, Also, we assume the flow to be inviscid, or we neglect the viscous effects, and for the time being, we assume the flow to be incompressible, which is also the second part of this problem, whether we can assume incompressibility or not. We will talk about it later. But first, we apply Bernoulli equation between points 1 and 2. Uh, the height z1 and z2 are same, so they cancel out. Velocity v2 is 0 because point 2 is the stagnation point. So the Bernoulli equation simplifies to that, just appears now on your screen as v1 square over 2g is equal to p2 minus p1 over gamma, where v1 is the velocity of helium at point 1, and pressure p2 minus p1, we know that pressure because a U-shaped manometer is connected to points 1 and 2. We need to find out the specific gravity of helium gamma, as we know the absolute pressure and temperature of helium flowing inside the pipe. We can apply the ideal gas law to find density of helium, and then from density we can calculate specific gravity, as specific gravity is equal to density times the acceleration due to gravity. To evaluate the pressure difference P2 minus P1, we can apply the hydrostatic pressure distribution analysis inside uh, the pitot static tube. Going from point 1 to 2, the fluid is at rest if we travel inside the pitot static tube. So if we assume the pressure P2 to be known starting from P2, if we go upward inside the helium, the pressure decreases by gamma of helium into height h2. Then if we further go upward a height h into water, the pressure again decreases by gamma w into h. Then we go downward, height h1 inside helium, and pressure increases by gamma helium into h1, and this equals to pressure p1. As gamma of helium is very small in comparison to gamma of water, because density of water is significantly higher than density of helium, which is a gas. So we can neglect both the terms gamma He into H2 and gamma He into H1, and we have P2 minus P1 is equal to gamma W into H, where we know the height h through U-shaped manometer. So after evaluating, the velocity v1 of helium comes out to be 203 feet per second. Now the question is whether we can assume this flow to be incompressible or not, or whether compressibility matters or not. To answer this question, we need to ask ourselves another question: what is the Mach number of the flow? Mach number is a ratio of two velocities, which is v is the local velocity and c is the local speed of sound. So we already know the local velocity of helium v, that is 203 feet per second. We need to calculate the local speed of sound c. We know the temperature of helium inside the pipe, and the local speed of sound c can be evaluated as c is equal to under the root k RT, where k is the ratio of two specific heats and r is the specific gas constant. So the Mach number comes out to be 0.063, which is significantly less than 0.3. So the flow of helium inside the pipe can be assumed to be incompressible. So we have another example problem that you can see on your screen. It's problem 3.61. There is a figure with the problem as well. The statement reads as water is siphoned from the tank shown in figure 3.61. Determine the flow rate for the tank and the pressure at points 1, 2, and 3 if viscous effects are negligible. So before going any further, we need to define what is flow rate. The flow rate Q is actually volumetric flow rate. Um, if we know the velocity of the flow and the cross-sectional area of the flow, we can define volumetric flow rate as Q is equal to VA. And if we know the volumetric flow rate Q, we can define mass flow rate M dot is equal to rho AV or rho Q. Both the mass flow rate and the volumetric flow rate are equivalent, but they are used in different industries. For example, for ventilation ducts, you will most probably use the volumetric flow rate to define the flow rate, and for oil and gas pipelines, you would probably use mass flow rate to define the flow rate. Before applying Bernoulli equation to this problem, we need to think about whether the four assumptions that we had talked about earlier are they valid here or not. The first one is that can we assume this process or this flow to be steady state? Of course, if the tank is sufficiently large enough, we can assume that the free surface moves very slowly and the pressure does not change over time, or if it does change, it changes very slowly, and we can assume this to be a steady state problem. Second, if the flow is incompressible, this is water, and we can safely assume this to be incompressible. We are being told that we should neglect viscous effects, and last but not the least, the points that we should select, we will assume that they lie along a streamline. To calculate the volumetric flow rate Q, we need to calculate velocity of flow in the pipe. If we can calculate velocity at point 2 or velocity at point 3, we can calculate the volumetric flow rate Q, because from continuity Q2 will be equal to Q3. If we try to apply Bernoulli equation between point 1, 2, and 3, we'll have more number of unknowns and just one equation, because at 1, 2, and 3, at this moment, pressure and velocity uh, both are unknown. So what we do instead is we choose two new points as they are shown on you in the figure now. They are labeled as point F and point 4. Point F is at the free surface of the tank, and point 4 is at the exit of the pipe. Both the points will have same pressure because both are exposed to the atmosphere. So we can assume both the pressures to be same and equal to 0 gauge. Velocity Vf will be 0 because we are assuming the tank to be sufficiently large. So we neglect Pf, Vf, and P4 in our Bernoulli equation that you can see written on your screen. Velocity V4 comes out to be 13.9 feet per second. So the volumetric flow rate Q through the pipe will be equal to Q is equal to V4 into A4, where A4 is the cross-sectional area of the pipe at point 4. Since we know that this hose or this pipe has a constant diameter that is equal to 2 inch, so we calculate the area A4 and multiply it with the velocity V4 that we have just calculated, that is equal to 13.9 feet per second, and we get the volumetric flow rate Q is equal to 0.304 feet cube per second. So now to calculate pressure P1, we apply Bernoulli equation between point F and point 1. As we had already talked, PF is exposed to atmosphere, so it is zero gauge. Um, Vf is zero because we assume the tank to be sufficiently large. V1 is zero because tank is not moving. And P1 comes out to be 499.2 pound per feet cube, and this is gauge pressure because we took PF to be zero gauge. So in order to find out pressure P2, we apply Bernoulli equation between point F and point 2, but we have two unknowns in one equation that we have written, that is P2 and V2. To find out V2, we apply continuity equation between point 2 and point 4. So the continuity between 2 and 4 states Q4 is equal to Q2, and since the area A2 and A4 is same because the hose has a constant diameter, so velocity V2 is equal to V4. So we write P2 in terms of V2 that you can see written on your screen, and the result comes out to be P2 is equal to 312 pound per feet cube gauge. This is gauge pressure again because we have assumed we have taken PF to be zero gauge. Similarly, we adopt the same procedure to find out P3, apply Bernoulli equation between point F and point 3, and we use again continuity. So V3 velocity at point 3 is equal to V4, and then we use this velocity to find out P3, which comes out to be minus 187.2 pound per feet scale.